Yesterday we were discussing how we can define amplitudes in string theory by summing all possible world sheets. We said that the summation that we are supposed to perform is only through all possible Riemann surfaces having specific number of handles and specific number of external punctures. Then we said that the space of all inequivalent Riemann surfaces having a specified number of handles and punctures is the moduli space of that Riemann surface. Then an amplitude or H loop contribution closed string scattering amplitude with n external strings having quantum numbers a1 to n can be understood as a integral of top form that we define in the moduli space of Riemann surfaces with h handles and n punctures, and then we are supposed to integrate this top form over the whole region in the moduli space. So that from there we realize that to understand the string amplitudes, the full string amplitude is given by summing all loop contributions, which can be understood as string coupling constant. Which one? It contains momenta, and it represents which state it is. Is it a graviton? These quantum numbers are not just momenta. But spin and all. Yeah, spin and all other informations. So from here we realize that to understand this or to evaluate this expression, we should understand more about Riemann surfaces, and we should know what is the space of all possible Riemann surfaces. So that means we should understand the moduli space of Riemann surfaces and its geometry. And for simply connected Riemann surfaces where you can find closed curves that can be string to a point. So you won't be able to find any single curve in this space in a simply connected space that can't be string to a point. So if you have such a simple Riemann surface, using uniformization theorem one can see that the moduli space is trivial, and we have only three possibilities: complex plane, Riemann sphere, and upper half plane. Any Riemann surface, any simply connected Riemann surface having a particular complex structure can be mapped to these three structures. Then we said that we need to understand multiply connected Riemann surfaces. That means Riemann surfaces having closed loops, a Riemann surface that has closed loops that cannot be shrink to a point. So this multiply connectedness give us lot more possibilities. We can define Riemann surfaces having several inequivalent complex structures. So our aim is to understand the moduli space of multiply connected Riemann surfaces. So here we realize that once we introduce a notion of universal covering, then we could understand the complex structure or inequivalent complex structures of Riemann surfaces by studying the structure of covering group.
So what was the goal you said for?
We want to understand the moduli space of multiply connected Riemann surfaces. That means we want to understand all possible inequivalent complex structures that we can enter on a two-dimensional multiply connected surface. To understand this situation, we introduced a notion of universal covering, where we said that we have a mapping from one Riemann surface, a simply connected Riemann surface, to an arbitrary Riemann surface. So pi is the mapping, and then we could define a transformation gamma, which we perform on the Riemann surface R tilde. And the gamma transformation takes a point C on R tilde to gamma of C. Then if you assume that pi of gamma or pi of gamma c is exactly equal to pi of c, then we call such a transformation as covering transformation. And all possible covering transformations form a group, which I denoted by capital gamma. So the advantage of
Conformal.
huh?
These are not conformal.
This is not a conformal transformation. No.
It is.
No, it's a many to one map.
Yeah.
Yeah. So that's why we are able to define a covering transformation.
Suppose I have a sphere.
Yeah.
And I have got 4 punctures in it.
Yeah. Yeah. So you have a sphere with 4 punctures.
What will be the modular space for this?
You can. Are you asking what is the parameterization, or in which way?
Yeah. See,
For parameterizing it, one way is that you could fix 3 points on the three punctures on the.
if I have 1 puncture,
Yeah.
I can make it into a plane.
Yeah.
Okay.
Yeah.
So if I have 2 punctures,
Yeah. So you can think of it like an infinite cylinder. Yeah.
okay. But if I have 4 punctures, it will be non-trivial, isn't it?
It's non-trivial, right? So still you can find a group gamma which can provide you this surface.
What will be the
What will be the R tilde? I will explain that.
meaning of
I will give an example. Actually, yesterday I gave some examples.
this is the simplest.
That is true. In fact, you can even understand long cylinders as obtained from some. This is not a simply connected space, right? So you can obtain this space from complex plane. So by taking, let's say you have complex plane with coordinate z. So if I use the covering map e raised to c, I obtain a long cylinder.
Yeah. But this is less than.
So this is less trivial. I mean less complicated.
Yeah.
But in this case, it's a bit more complicated.
Yeah. 4 is
Yeah, even 3 is actually non-trivial.
because if it is up to 3, you can get.
No, if you have a thrice punctured sphere, still it's non-trivial.
Yeah.
So you can obtain thrice punctured sphere from upper half plane by moding out to.
Yeah.
Yeah, that I will explain. I will explicitly state the covering group for that.
4 will be the.
So yeah, 4 is a situation where you have a non-trivial moduli space. That's true.
So, since it's a many to one map,
Yeah.
R pi is many to one. This is some
Gamma,
yeah, pi
pi, yeah, it's a many to one.
many to one. So
Yeah.
in some sense there are multiple copies of R.
So actually, gamma is actually taking you from one point to the copy image, right? So C and gamma C map you to same point. That's why it's a many to one map.
Yeah. So in some sense there is multiple copies of R inside R tilde.
Yeah,
Those copies are connected by gamma,
exactly.
right?
Yeah.
So, and this relation between pi and gamma is enough to prove that gamma is a group.
Yeah, you can introduce one more transformation gamma 1, gamma C. So this becomes pi gamma 1 C, right? If gamma 1 is a covering transformation, right? Then this becomes pi of C, right?
But gamma may not have an inverse.
A gamma may not have.
Have an inverse, so we are assuming it is a.
Yeah, it can have an inverse, right?
Yeah, but it's an assumption at this stage that it has an inverse.
No, you can define an inverse for it, right? I mean, there's nothing non-trivial happening here, right? So that you won't be able to define an inverse, right? So the idea is to define, think of Riemann surface as obtained from a simply connected Riemann surface. Once you have such a map, you will be able to find transformations which together form a group, capital gamma. Now R can be understood as R tilde divided by or quotienting with group gamma.
Maybe a silly question. What makes gamma a discrete group here? I mean, is there some easy way to say it?
You mean by discrete? Do you mean the number of generators are? Yeah. So the easy way to do is see is the following. So you have a Riemann surface, and you can see that here you are so you have a covering space, and in the covering space you are identifying 2 points, right? And if you look into the image, what is happening in the Riemann surface, you are actually going through a non-trivial cycle, right? Now on a Riemann surface, you have some finite number of cycles, independent cycles, right? And any cycle on a Riemann surface can be obtained from some number of independent cycles, right? So that itself says that gamma must have finite number of generators.
Because R tilde itself is a Riemann surface.
Exactly. And R is a Riemann surface with some specific number of handles and punctures. That itself says that you have a specific number of independent cycles are there on the Riemann surface R. So from there you can see that the group gamma is discrete, right? So we can think of R as obtained from R tilde by identifying points on R tilde which is related by a transformation that belongs to the group gamma.
There are certain transformations under which Riemann surface is also invariant. For example, SL2R and SL2C surface.
So those are the things which you use to fix 3 points, right?
Yeah, right. So that is not still playing here any role in this statement.
No.
Those are complified.
Yeah. Now once you have that statement, then the good thing is that you will be able to identify different Riemann surfaces by looking into the group gamma, right? So all the information about once you fix the covering space, universal covering space, say C or H, then you can identify the Riemann surface R with the group gamma. So yesterday we said that so to understand multiply connected Riemann surfaces, we have a generalization for uniformization theorem. So that's the statement is that whenever you have a multiply connected Riemann surface, you can obtain that surface from a simply connected Riemann surface by quotienting with some group gamma. So the
C will be the simply gamma.
Yeah. So it's like you have 2 copies of. Yeah, that's true. Yeah. So that's why you define hyperelliptic surfaces. Now let me look into Riemann surfaces which is other than C, C hat, C minus 0 and tori. So these are the surfaces which are known as exceptional Riemann surfaces.
C hat is C is a complex plane and C hat is
Riemann sphere. It's just a nomenclature. I just want to look into Riemann surfaces that are not exceptional, because anyway C is simply connected, C hat is simply connected, C minus 0 can be obtained from complex plane by using e raised to C map, and tori can be obtained from complex plane by moding out with this lattice group. So all other Riemann surfaces with punctures or genus can be obtained from upper half plane. So this is the function.
See it or giving a handle to
Exactly.
to a sphere.
Yeah. So this is a Fuchsian uniformization theorem statement. Any other Riemann surface, any Riemann surface that is not of an exceptional type, you can obtain that from upper half plane by moding out with an appropriate group gamma. Now let me explain what is gamma. For that, it's useful to introduce a Poincare metric on the upper half plane. It's given by ds square h equal to dc mod square divided by imaginary part of c whole square. So c is the coordinate on the upper half plane. Now you can easily observe that this metric has a symmetry. So if I take c to gamma c defined by AC by B, CC by D with AD minus BC equal to 1 and A, B, C, D belongs to R, then such a transformation will keep this metric invariant. And these elements A, B, C, D form a 2 by 2 matrix, and they together form the group PSL2R. So PSL2R is the isometry group for this metric, for Poincare metric. Yeah. Then a group gamma, which we call as Fuchsian group, can be understood as a subgroup of PSL2R. So take a subgroup of PSL2R and then mod H by that subgroup, then that corresponds to a Riemann surface, which is not of an exceptional type. So the statement is that for any Riemann surface R that is not of exceptional type, we can find an appropriate subgroup of PSL2R. And this will provide us the Riemann surface of our interest by identifying points on the upper half plane. So that's a statement. So let me give you an example. Do you have better desktop?
Actually, this is the best.
What is the best I can?
No, best form of the code.
Oh, okay. Okay, it's fine.
In the testers,
So before going to the details, let me say the geodesics on upper half plane with respect to the Poincare metric are half circles with endpoints, two endpoints on the real axis, and they end perpendicularly on the real axis. So you have half circles. These half circles are geodesics of this metric, and other possible geodesics are straight line coming from I infinity, and that land on the real line perpendicularly. These are the two possible geodesics that you can have. Now let's consider point C on upper half plane and then perform a Mobius transformation or a PSL2R transformation gamma C. So you take your point C to gamma C. Oh yeah, sure. Thank you.
I just want to any R that is non-exceptional,
Yeah.
you obtain by H by gamma. Gamma is a
Subgroup of PSL2.
PSL2.
Yeah,
That's a statement.
that's a statement.
And here,
So here I have upper half plane with Poincare metric on it. I'm stating that so that you can have two kinds of geodesics on the upper half plane with Poincare metric. So these are half circles or straight lines going to I infinity, and that land on the real line perpendicularly. These are the only two possibilities. So you can solve the equations of motion and then figure out.
so for the half circle,
Yeah,
the initial point on the real line,
yeah.
that initial condition is same as the other one, right?
So you have two flows. So this is something which you can easily.
Initial condition is
Yeah, here, right?
same. The initial velocity is the same,
Yeah.
but you end up getting two geodesics. Sorry.
No.
Position is all is
No. You have two possibilities. Either it has two fixed points, which is on a real line, or you have.
If you take from on the real line,
Yeah.
take a perpendicular,
Yeah.
and take the initial tangent vector,
Yeah.
what will be the geodesic?
It depends on, you have to solve it and see, right?
The metric, yeah, that's it.
So that's a metric. You can just.
You know, I'm asking what is the answer. If you take the metric, what is the answer?
So these are the two possibilities.
How can you have two possibilities? It's the same initial condition.
So you have to see. You take the second derivative.
See, you write down the metric in dx square dy square.
Any radius is okay. So infinite radius.
Infinite radius, right?
See, you write down.
So that means you need more I mean, it's like infinite velocity in some sense.
No, I thought initial position and initial velocity will uniquely choose.
So then you have to see which one.
At the boundary, it always ends perpendicular.
Yeah.
You control.
Yeah.
See, write down dx square plus dy square upon y square. That is the metric for the problem.
So y goes to 0 at the boundary.
I see,
the boundary.
So the initial condition does not uniquely choose the geodesic.
At if it is on the boundary.
I understand.
Okay.
So let's consider point C and then transform to other point gamma C. So gamma is an element of Fuchsian group, say. Then you can try to draw a geodesic that connects C and gamma C. So the statement is that the length of this geodesic can be written down in terms of the generator gamma. So let's say gamma is a 2 by 2 matrix A, B, C, D. Then say the length of this geodesic is L gamma, the minimum length. Then for cos h square, L gamma by 2 is given by trace of gamma whole square, or you can think of this as A plus B whole square. This is a relation one can prove. So you have a point C and then map it to a point gamma C and then find the minimum length geodesic that connects these two. Then say that the length of that geodesic is L gamma. Now you can find a relation between L gamma and the trace of the transformation gamma. So this is precisely that relation. So you can relate a transformation gamma with a geodesic on the upper half plane. So this is for cos h square, cos h hyperbolic, L gamma by 2. Another one. So this is the statement. So you can identify a transformation with a geodesic on the upper half plane. So what you can do is you state point C and gamma C, draw a geodesic, compute its length, and then minimize it by varying C.
But how do you do it? How do you get this
Cos hyperbolic, right?
Cos hyperbolic of
L gamma by 2 whole square equal to A plus D. Yeah, L gamma is a length of the geodesic. So you should understand that take an arbitrary point C and then transform it to gamma C, then compute the length, it's some length L, and then minimize that length with respect to C. Right? So you will find a particular point on the upper half plane for which L is small, minimum. And that minimum length can be related to the trace of gamma. So this is a relation. Now it's actually useful.
You are fixing gamma Z for second statement.
No, so I start with C, arbitrary point. Huh?
Trace square of the matrix.
Yeah, trace square of the metric. Yeah, trace of gamma whole square. This is like A plus D whole square.
So I didn't get it. It doesn't depend on C at all.
Yeah. So the point is that you start with C, and then you compute find the transformation gamma C, find the point gamma C on the upper half plane. Then you can use the metric to find what is the length that connects the point Z and gamma C. Right? Then you get a length that is a function of Z. Right? Then you can minimize it.
Oh, I see.
Well, there is one geodesic.
So you can vary C, right?
So the geodesic as a function of Z being
minimized, right?
The geodesic length.
So or in other words, so you said that we have some so you look into the Riemann surface. What is happening? Yeah. So that
will correspond to this value.
Yeah, that corresponds to A plus D whole square.
L gamma minimized.
Okay, fine. So that's a relation.
But has C a unique solution? Probably not, right?
No, this is a relation.
Translate this along the real direction, still be a geodesic.
Yeah, still a geodesic, right?
With that any point.
I can translate it or go up, right?
Oh, there it won't be because imaginary metric depends on the imaginary part.
Which one?
Your metric
Yeah, depends on the imaginary part.
translated in the right towards actually it doesn't change.
Doesn't change, right?
Yeah, but
So-
gamma z will change.
That is true.
Gamma z will simply not be translated, right? Gamma z will be.
Oh,
Yeah.
Gamma z.
Which is not.
So you have to connect C and gamma C.
So therefore, probably z is unique.
So in other words, what I am trying to see is I'm trying to connect a transformation gamma that I perform on the upper half plane to a geodesic on the Riemann surface. So this transformation, huh?
It's a very unique geodesic.
Yeah, to a unique geodesic.
Because z is unique.
Z is unique, right? So this kind of an identification, I said that corresponds to a non-trivial cycle on the Riemann surface, right? After I mod out H by gamma, right? Then my statement is that in that homotopy, I can find a minimum length geodesic, and the length of that minimum length geodesic is precisely related to the trace of transformation gamma this way. So transformations, elements of Fuchsian group can be related to a simple closed geodesic on the Riemann surface that you obtain, and then you can compute the length of that minimal length geodesic by finding the trace of gamma.
But how did you make this choice? Push a parabolic.
Oh, it's actually computed. You can compute it and then see it.
This everything is.
See, I can compute it from group theory waveform.
No, I can just take this metric and then
I can write down the metric.
yeah,
And then it's part of the trace.
yeah.
But
Now you can take the.
point, I don't know how to do it.
See, you have a metric, right? You know the metric, right? And then you are supposed to integrate this metric from C to gamma C. This is something which you can do, right? So you compute it, and then that provides a length, which might be a function of the point C,
What is dy by gt is
dy by v, which is actually
the determinant.
imaginary part of C, right? So from metric you can work it out.
Yeah, imaginary part of the metric is 0, 1.
Yeah.
So when L gamma is 0, this is A plus T squared.
When L gamma is 0, you have A plus D equal to plus or minus 2. So those transformations which has trace plus or minus 2 are known as the parabolic transformations. So they represent a puncture on the Riemann surface. A transformation that has trace more than or equal to that has trace more than 4 or trace square more than 4 corresponds to a non-trivial simple closed geodesic on the surface. So such elements are known as hyperbolic elements. A hyperbolic element of Fuchsian group corresponds to a non-trivial simple closed geodesic, and a parabolic element in the Fuchsian group corresponds to a puncture on the Riemann surface.
Is it hyperbolic and parabolic?
So a hyperbolic transformation gamma has trace gamma square greater than 4, and a parabolic transformation has trace gamma square equal to 4.
Yeah. But why this nomenclature? There must be some hyperbola or parabola associated.
Then you are elliptic.
Here you have elliptic. So I don't want to look into that. So just think of this as some nomenclature, right? So you have two kinds of elements that has trace greater than 4. They represent a simple closed geodesic on the Riemann surface. If they have trace gamma whole square equal to 4, then that represents a puncture. So
Understand why the geodesic is closed?
so you have an identification. C is identified with gamma C, right? On the Riemann surface, you have a closed curve, right?
That's all right, but so far you are just talking about, you are not identifying anything, you are just saying
I said that I'm considering this Riemann surface, right? And gamma the small gamma belongs to the capital group capital gamma, right?
Because I was thinking gamma, you are talking of gamma as an arbitrary element.
Arbitrary element of no, not an arbitrary element of PSL2, because here I already choose that a Riemann surface can be obtained from this function group gamma, right?
Okay, but this statement that you made is not true for arbitrary PSL2R.
For arbitrary PSL2R, I mean subgroup of PSL2R transform, right?
No, so you made a statement.
First you have to define your Riemann surface, right? So you define your function group and then take an element from that function group, then make these statements. I don't want to, so this statement is true anyway.
This statement is true anyway.
Independent of whether you want to have a Riemann surface or not.
Then when you identify Z and gamma Z,
Yeah.
either be a closed geodesic or not.
On the Riemann surface, right? So my my main motivation is to study the Riemann surface, right? So then when I have C and gamma C, I think of them as identified, because I want to think from the point of view of Riemann surface. So this transformation provides you a closed curve on the Riemann surface, and then minimize its length.
For every element in that gamma, whatever you have chosen, that gamma to be a subgroup of PSL2R.
Yeah.
For every element you can do this operation.
That is true.
It will give you either
Hyperbolic or
thing
or parabolic.
puncture.
That's true.
That's puncture, right?
Right.
Length goes to 0, it is simple.
Length goes to 0. So if you have a simple closed geodesic, then you can make length goes to 0. Then you are actually looking into the degeneration. So there you get 2 punctures. But I can have external punctures, right? So to start with, I can have Riemann surface with punctures.
You were saying Z and gamma Z are identified because I think so. They are the different fibers for the same point on the.
Yeah, that is true. That is true. That's true. So they are the copies of same point on the upper half plane.
So, this card, the closed card that you have drawn,
Yeah. Yeah.
there are 2 sides of it when it is non-zero.
Yeah. Right.
But when it goes to 0,
That corresponds to degeneration of the Riemann surface.
yeah, but it doesn't have 2 sides. It just goes to 1 point, right?
You can think of this as a long cylinder, very long cylinder.
So it has
Right.
two sides.
Yeah, so you can, so the thing is that this part of the Riemann surface will not know anything about this part, right? So you can think of these 2 sides as 2 independent Riemann surfaces.
In that picture, could you identify these 2 lobes, these 2 portions in the geodesic picture?
In the geodesic picture, what's the statement?
How do you see these 2 regions?
Yeah.
How do you see in that picture?
In this picture, so like you can, first of all, I haven't drawn the fundamental domain for the group gamma. So I mean, I will explain that, or otherwise you can work it out yourself. So the point is that you can get any Riemann surface that is not of exceptional type from upper half plane. That's the statement. This looks like a trivial statement, but it's a very powerful statement. And there is the observation that allows you to make calculations on Riemann surface. So here you see, you want to study a Riemann surface, and you want to do calculations on Riemann surface. How will you do it? You want a representative, right? So this idea provides you a connection between Riemann surface and upper half plane. So whatever calculation that you want to do on Riemann surface can be done on upper half plane. This is actually a big gain or big jump. On upper half plane, whatever calculation that you are supposed to do is just trigonometry. So you do some simple trigonometry, and that can be translated to a calculation on the Riemann surface. So that's a nice thing. So let me go.
You could change the metric on the upper half plane also.
Yeah, you could, no, I don't want to change.
Statements will change corresponding to it.
I want to stick with this metric. So then it becomes more powerful. Now let me give you an example.
I have so many questions, but I'll ask you a question. Given a gamma,
Yeah,
given a capital gamma,
capital gamma, right?
how do I write a formula for Euler character?
Euler character, you mean?
Of the resultant Riemann surface, so the chi that you were using. Yes.
So the Euler character is related to the number of independent cycles that you have, right? So you can, yeah, so you can just count the number of independent elements in gamma.
which have.
So that is related to the Euler characteristic.
There's no simple form.
You have to just find the independent number of transformation that you have. So that's it. So that question is easy from the point of view of Riemann surface, right? You have to just see.
True.
Here also, since I made a connection between the
Upper half plane and the capital gamma, right?
Yeah. So then you have to just look into the group gamma, the capital gamma itself. See how many what is the number of generators, right? That will help.
Fundamental group of R will generate capital gamma.
That is true. So let me give you a simple example how these things are working.
It means AD minus BC is equal to
1. Yeah, not equal. So it's equal to 1. So then let me give you a simple example for this construction. I want to construct thrice punctured sphere from upper half plane. This is what I want to do. So the group Fuchsian group is generated by two elements that corresponds to, so you have gamma 1 and gamma 2. You can use these two elements to construct the group that corresponds to a thrice punctured sphere. So let me tell you what is gamma 1. The action of gamma 1 on C.
What are these three? These are the punctures?
These are three punctures. Three punctures.
Three punctures should be trivial case.
Trivial. I mean, from the point of view of moduli space, is trivial, but still I have to construct it, right? Since it's not an exceptional one. So the transformations that I'm supposed to use for generating the group for three punctured sphere are the following. So gamma 1 acts on a point on C on upper half plane as follows. So it takes you from C to C minus 2, and gamma 2C C plus 1. With these two transformations, you can generate a group, and then take that group and then mod out upper half plane by that group. Then you get thrice punctured sphere. So since you have a group, you can find how things are identified on the upper half plane. By that I mean we can try to figure out what is the fundamental domain for this group gamma on the upper half plane. Say let's look into the first transformation, C going to C minus 2. That identifies point minus a line minus 1 to point line plus 1, right? And then C going to C by 2C plus 1 does the following identification. It identifies points on two circles, half circles. So you have this kind of an identification. A point on this half circle will be identified to a point on this half circle. So you get this as the fundamental domain. Now you can see that C going to C minus 2 identifies this line with this line, so that you start getting a cylinder, right? A cylinder that goes to I infinity. And then here you are identifying this point and this point. So here also you are getting a cylinder. Then this one is identified with this, so that you get the other long cylinder. So these cylinders goes to infinity. So that's the way you get thrice punctured sphere, by performing an identification. Now you can also generate a pair of pans. A sphere, hyperbolic sphere with three borders. Say the border length are L1, L2, L3. So you can find the appropriate Fuchsian group gamma. So you can find the generators in terms of length parameter L1, L2, L3. Huh? Which one? So, this one, right? So if I do identifications on the fundamental domain, so you have fundamental domain, and then in strict terms you are not supposed to include two boundaries, right? Because this boundary is identified with this boundary, right? Once I do this identification, so you are doing a folding, right? So that you generate this cylinder. Now if I do this identification here, I have this point. And when I do identification here, so this identification is a combined identification, so that you obtain this cylinder. So that's the way you obtain a thrice punctured sphere from upper half plane. So that's a example. So you can go ahead and then so similar construction can be done for pair of pans. A genus 0 hyperbolic surface with 3 borders, and you can specify the boundary lengths for the borders. Then corresponding to that, you can find a Fuchsian group gamma p.
So there, you can calculate the lengths of these circles also, right?
Here in first example, length of the cycles, there is so you will see that there is no non-trivial geodesic on thrice punctured sphere that has finite length. So that's why you have, so these two transformations are parabolic transformations. So you compute the trace of it, it's just and take the square, is just 4. So the
that's why they are punctures. So
exactly.
So this you are talking of like circle that's little this. Actually a puncture.
It's actually a puncture. It goes to infinity.
So then the gamma will have these L1, L2, L3 parameters.
Yeah.
Involved.
If I want to construct
This one.
gamma p for the pair of pans, and here you have transformation 1 0 2 1. So you see the trace is 2.
Yeah.
So that's why these are parabolic elements. So they represent punctures. So that's a basic idea about.
You will not work out gamma p.
You can work out. I have the expression. I do not write it down. And then at the end you can find what are the generators for gamma p, and then take L1, L2, L3 goes to 0. You will reproduce this group. Now, so that's the way you construct an arbitrary Riemann surface. Now let us ask. So we have a construction for arbitrary Riemann surfaces. Now we want to go ahead and then see what do you mean by inequivalent Riemann surfaces. By inequivalent Riemann surface, we mean that we have two dimensional surfaces having inequivalent complex structures. So we should have a specific, or we should have efficient tools for comparing two complex structures. If you are not able to compare two complex structures, we won't be able to find the space of all complex structures, right? So that's the next thing that we want. How will we compare two complex structures? For this, it's useful to introduce the notion of quasi-conformal transformations. This can be understood as generalization of conformal transformations. So let us consider a simply connected domain D. Then assume that we have a function f of c bar that is defined on this domain D. Now we assume that the derivative del f by del c and del f by del c bar are well defined on this domain. Then we again assume that if you take del f by del c bar and take the mode, it should be less than or equal to some number k del f by del c, and k should be a real number that belongs to the interval 0 1. So such a transformation that you perform on domain D is known as a quasi-conformal transformation. So this is the definition of a quasi-conformal transformation. It can be a conformal transformation, or it may be a general transformation. But the condition is that if once I take the mode of del f by del c bar, it should be less than the mode of del f by del c. What does this mean? This means that if I compute this object del f by del c mod square minus del f by del c bar mod square, it should be greater than 0. And what is this? This is Jacobian of the transformation f. So you want all those transformations on the domain D that won't change the orientation of domain D. So such a transformation is known as quasi-conformal transformation. So you can change domain D to something else without changing its orientation. So all such general transformations are known as quasi-conformal transformations. So since you are
Transformation is Z going to F of Z bar, Z bar.
F going to?
What is the transformation of Z?
Z going to, yeah, Z going to F of C bar. Right? It's not a conformal transformation. It can be conformal transformation. It can be a transformation that is not conformal as well.
Okay, it's a transformation which keeps the
Orientation same, orientation fixed. So when F is not conformal transformation, that means we are trying to change the complex structure of domain D. So that's a statement. So you could think of. That's true. You could just say that it's just less than del F by del C. So here I allow the possibility that K can be equal to 0 as well, so that it's more clear, right? So it can be a conformal transformation as well. So let's assume that D is a domain in the Riemann surface. When I perform a quasi-conformal transformation in that domain, that can change the complex structure of Riemann surface. So in that sense, in general, you are staying on a Riemann surface R, and in some region you are performing a transformation that will change the surface itself. So that way you will be able to go from one complex structure to another. So that's why, yeah. So you always work with a Riemann surface R, and then choose a domain in R. Now in this domain, you perform a quasi-conformal transformation. Keep all other domains, the complement of D in R untouched. Once I do that, what I gain is I'm actually changing the complex structure of Riemann surface. By changing the complex structure of Riemann surface, you mean you are generating another Riemann surface S. Right? So by performing transformations on the Riemann surface itself, which are not conformal, you can change the complex structure. Right? So that means you have this pair F, a quasi-conformal transformation.
If you give this transformation in D, in A's, so that part is not conformally connected to.
Because anyway, there is some domain.
Match that with the neighborhood.
Yeah, every domain you should be able to find a mapping, right? So if you want to say that R and S are same Riemann surface, every domain in R should be we should be able to map every domain in R to S using a conformal transformation. So here in this part you can find a transformation that take you from R to S, which is conformal.
I understand, but I'm saying that D has a boundary.
Yeah, D can have a boundary.
So F has to go to Z, something has to go to 0 there to match with the neighborhood.
No, you could say that F of C bar is equal to C at the boundary, right?
So it has to go to there.
Yeah, it has to go to the or some conformal transformation GC.
Or any one.
Yeah, GC.
So on the boundary F should be fine.
Yeah, so that it smoothly matches, right? So this is a this is a transformation that changes the Riemann surface. So you can think that you have some arbitrary quasi-conformal transformation that take R to S. R is a Riemann surface and S is another Riemann surface. Now we say that, and let's say you have another transformation. So you have one transformation F1 that take you from R to S, and F2 that take you from R to say some S2. So you have F1 take R to S1 and F2 take R to S2. So we say that S1 and S2 are equivalent if F1 F2 inverse is a biholomorphic map. So that means you will be able to find a conformal transformation from S1 to S2. Right? So you have two transformation F1 and F2. If they can be connected through a conformal transformation. That means F1 and F2 are not really inequivalent transformations. They are equivalent transformation.
If it didn't preserve the orientation, you wouldn't probably cannot go to a conformal transformation on the boundary.
No, it's not that. If I change the orientation, I change the Riemann surface itself. Right? Then I don't have the Riemann surface. So I'm working with a.
So you change the orientation and still go to conformal transformation on the
So then you are thinking about Riemann surface that does not have any orientation. I am working with Riemann surface having an orientation, right? So if the
mathematically it is possible.
I mean, if you are including unoriented Riemann surfaces as well, I am working with oriented Riemann surfaces. I don't want, so I can't change the orientation, right? So see, so you have all possible quasi-conformal transformations so there are so many possibilities. Let's list all possible quasi-conformal transformations that you can perform on R. And some of the quasi-conformal transformation may be doing the same job if they are connected by a conformal transformation. And this connection, so if two are connected by some conformal transformation, we say that they are equivalent. So the Teichmuller space of Riemann surface can be thought of as all inequivalent possible quasi-conformal transformation. So which we denote by R. So you choose a based Riemann surface R and perform transformations on this surface. So the Teichmuller space is a space of all inequivalent quasi-conformal transformations that you can perform on R.
This is the definition of Teichmuller?
So this is the definition of Teichmuller space.
What is it you are saying? Or inequivalent?
All inequivalent.
Quasi-conformal transformations.
Or all inequivalent quasi-conformal transformations. They form the space. They form the Teichmuller space for Riemann surface.
So that means and what are quasi-conformal transformations?
Oh, quasi-conformal transformations are all possible transformations that you can perform on Riemann surface without changing its orientation.
So they are orientation
Preserving mapping.
and Teichmuller is can change the orientation.
No, within Teichmuller space you don't change the orientation.
But you say there are non-quasi-conformal.
No, I said that all inequivalent quasi-conformal transformations form the Teichmuller space for Riemann surface. And here you choose a specific base space R, and you are performing transformations on that base space.
You said inequivalent quasi-conformal.
Yeah, equivalence condition, right?
Yeah.
So if two transformations can be related, if you can relate them by a conformal transformation, up to conformal transformation, right? Exactly, identifying up to conformal transformation. That inequivalent class will provide you the definition for Teichmuller space.
Conformal transformations preserve the geodesics.
Yeah,
And this condition that you write down
yeah.
is a condition on something like an area.
It's a condition on the orientation.
Huh?
It's a condition on the orientation on the surface, right? Yeah.
Not
So
the-
your handedness,
Not an area.
not on the area. It could change the area, right? So it's just a Jacobian for the transformation. If the Jacobian is greater than 0, you preserve the orientation.
Area is not preserved.
Area is not preserved. So that's a definition for a quasi-conformal transformation and the definition for Teichmuller space. So using quasi-conformal transformation, we are able to at least give a formal definition for the Teichmuller space. Now we will make it more rigorous, or we will make it more practical.
All possible inequivalent
Quasi-conformal transformation. So let me give you an example for quasi-conformal transformation. So FCC bar equal to C that belongs to upper half plane. So we are performing a transformation on the complex plane. On the upper half plane, we
You put this T here.
which one?
About there.
Yeah,
That's a T, no?
it's a K.
Here.
Some number K.
Any conditions on K?
Yeah, the condition is that K should belongs to this interval 0 to 1. It's a real number which is less than 1. And less than 1 and greater than or equal to 0. So that condition says that this is a map that preserves the
K quasi-conformal.
K.
K quasi-conformal. If K is equal to 1,
K is equal to 1 is not allowed.
then it is conformal.
Yeah, K is equal to 1 is not allowed. That means you have Jacobian equal to 0. You don't want that. K equal to 0 corresponds to a conformal transformation, right? So then del F by del C is equal to 0, right?
And K is equal to 1 is not allowed.
K is equal to 1 is not allowed. So you have, I can write down an example for quasi-conformal transformation that you perform on the complex plane. So on the upper half plane, let's say f of c bar equal to c. It's not doing anything. It's an identity transformation. And the lower half, say it perform the transformation x plus I capital K y, where x plus I y, that belongs to the lower half plane, h star plus real line or c minus h. So you have lower half plane with real line where we perform this transformation s plus I k capital Ky, where k is greater than 1. So then you can
see if it is 0,
yeah,
then that means I am considering holomorphic.
Yeah, you are considering a holomorphic transformation.
If I consider the z bar,
Yeah,
then they are anti-holomorphic.
yeah, they are anti-holomorphic.
So you are distinguishing between holomorphic and anti-holomorphic.
Yes, exactly. Yeah. So if I change C to C bar immediately, that changes the orientation, right? Which I don't want. That's why I always want the component of C bar to be less than the component of C, so that I can always keep the orientation same.
So you mean the whole system distinguishes between holomorphic and anti-holomorphic?
No, his transformation is z going to f. So holomorphicity means f is not del f del z bar is 0.
Yeah,
So that's a conformal transformation. K equal to 0
it's a conformal transformation, right? So anyway, so you can.
Continuous and y equals 0.
Yeah, so that's a good thing about quasi-conformal transformation. You could do jumps. You can make jump. So that's why I mean, it's not necessary that they should immediately match. In fact, at the end, I will explain a particular way of understanding Teichmuller space where I have quasi-conformal transformation, which I can do abruptly.
That's not don't distinguish between holomorphic and anti-holomorphic.
No, I'm just saying that just forget about holomorphicity. I'm just making a statement that with respect to any coordinate that you define on the Riemann surface or the two-dimensional surface, you want to perform a transformation that doesn't change its orientation. So that's the only statement that I want to make. And because you see here, you see that I am trying to distinguish between coordinate c and c bar, because I define orientation with respect to c and c bar. So that's the reason why I have to I have to emphasize c and c bar.
So
Right?
here del f by del c bar is discontinuous at y is equal to 0.
Yeah.
Y is only.
It's like, so that's the definition for quasi-conformal transformation. It allows that as well.
Del f by del z bar can be discontinuous.
Yeah, I mean on a measure 0 points, right? Almost all points del f by del c bar and del f by del c should be I mean, it should not have any discontinuity, but you can introduce discontinuity as well. So that's why quasi-conformal transformation can be thought of as some twist and gluing kind of transformations.
What bothers me in physics, when you consider this Heisenberg group, you remove the anti-holomorphic transformation.
Yeah.
Not holomorphic.
Yeah, that's true. So even in string theory, you can consider such transformation where you have unoriented string theory. I'm just looking into oriented closed string theory. That's why I'm only looking into these possibilities. I'm not saying that there are no other possibilities. For my situation where I have closed Riemann surfaces with punctures with definite orientation, there is a possibility that I want to allow.
So you cannot apply to this the physical situation where you consider the canonical quantization. It is all anti-holomorphic.
No, that is true, but I have a specific problem in my mind, right? I want to study string theory and closed string theory. If I am studying type 1 string theory, I could allow all the other possibilities. I don't want to discuss type 1 here. So so this is the definition for Teichmuller space. Teichmuller space is a space of all inequivalent quasi-conformal transformation. Now I have to utilize I introduce this notion of Fuchsian uniformization, right? Where so the main motivation for introducing that was to use the fact that upper half plane is more manageable compared to the whole Riemann surface, right? So I should be able to find a way to characterize all this possible inequivalent quasi-conformal transformation in terms of a condition on the upper half plane. That's the thing which I want to attain or achieve. So let me define, for that I can introduce a notion of Beltrami differentials. So in fact there is nothing more in Beltrami differential. It has exactly equivalent information that F has, quasi-conformal transformation has. So you can define a Beltrami differential with respect to a quasi-conformal transformation mu f as del f by del c bar divided by del f by del c. If the transformation f is a conformal transformation, Beltrami differential is 0. So that's the statement. Now,
So the Beltrami differential will be discontinuous.
Beltrami differential, yeah, here, for here, right? So here you have 0 on the upper half plane and some finite value on the lower half plane. So that's fine. So those kind of discontinuous things are allowed.
By z bar.
Oh, here del f del c, z bar divided by del f by del c. Yeah. So here you can think of k is as mode of del mu f, right? So the condition is that, so let me reverse the whole problem. I can start with a Beltrami differential, and a Beltrami differential, if the value of mode of Beltrami differential in a region, if it is always less than or equal less than 1 and greater than or equal to 0, then it is always possible to find associated quasi-conformal transformation. Now if I fix some normalization condition for the quasi-conformal transformation, oh sorry, mu f, right. So
No, I'm asking for a notation. What?
it's fine, it's okay. So so the point is that if whenever I have a quasi-conformal a Beltrami differential whose absolute value is less than 1 and greater than 0 in a region, then it's always possible to find a quasi-conformal transformation associated with that Beltrami differential, such that that quasi-conformal transformation is related to the Beltrami differential this way. And that identification is unique. Once I specify that, say I am working on a complex plane. If I specify that, that quasi-conformal transformation is not acting on point 0, point 1 and infinity, or if that transformation is fixing 0, 1 and infinity, then the relation between Beltrami differential and quasi-conformal transformation is 1 to 1. So the space of Beltrami differential can be understood as so if I take all inequivalent Beltrami differential, that again provides me the Teichmuller space.
Inequivalent means the sign, is it?
It means?
Inequivalent means what?
Inequivalent means that I should get a quasi-conformal transformation. So let's say I have Beltrami differential mu and nu. Find the mu and nu and mu. If I find the quasi-conformal transformation associated with nu, which I denote by f nu, and I can compute the quasi-conformal transformation associated with f mu. If f nu and f mu are not relatable to each other by a conformal transformation, then I say that mu and nu are inequivalent, right?
They are not related by
conformal, just a conformal transformation, right? If I can relate f nu and f mu by a conformal transformation, they are equivalent. If they are not relatable by a conformal transformation, they are inequivalent.
So they are conformally unequal.
Conformally unequal, right?
But quasi-conformal is there.
It's there, yeah. Both are quasi-conformal.
So you are looking for
Inequivalent.
only unequal.
Inequivalent, exactly.
So the statement was that if you look at any f which fixes 0, 1 and infinity, then there's a unique correspondence between mu f and f.
Exactly, yeah. So I can start with mu, solve this differential equation, obtain the conformal transformation up to this with this normalization, then the relation between mu and f is 1 to 1.
So anyway, you just need 3 points.
Exactly, right. So this.
And what was this inequality? What was that?
Here.
That, yeah.
So here I am assuming that the absolute value of mu of in a domain should be less than 1. So this is the same this statement, right? So far, I mean, I was just going from one quantity to another. I didn't gain anything. So what I should do is the following. So I can now I have to define a Beltrami differential on a Riemann surface using the idea of Fuchsian uniformization. Then things will become more powerful. So let's consider a Riemann surface R and assume that R can be obtained from upper half plane by moding out with this group gamma, and the group gamma can be is called as the Fuchsian model for Riemann surface R. So assume that you have a quasi-conformal transformation on the upper half plane, mu of C, where C belongs to upper half plane. This differential or this object is called as a Beltrami differential on the upper half plane with respect to gamma only if it has a specific transformation property. So mu of gamma C must be equal to mu of C multiplied with some transformation factors, d gamma C by dc divided by d gamma C bar dc. So only if Beltrami differential has an appropriate periodic identification on the upper half plane, then only you say that Beltrami differential is a Beltrami differential defined on upper half plane with respect to the group gamma. So when you have this identification, you can think of the Beltrami differential as a differential on the Riemann surface, right? So when you go along a homotopy cycle, some non-trivial cycle, you come back to the same value up to some factor. That's the way you define a differential, right? So on the upper half plane, if you are able to find such Beltrami differentials, then that can be understood as a differential on the Riemann surface. So you are just saying that.
What gives you this kind of composition law?
So see.
How do you get this particular composition?
So you can look into this definition, see how this is transforming with respect to C, right?
Under what?
Under C going to gamma C. So you can see that this object is actually a differential, not a function.
But here you use a very specific kind of gamma Z, or gamma Z can be any holomorphic.
Gamma C should be an element in the group gamma.
This I understand.
Yeah.
Just for this composition law to work.
Or this composition law, if I can have arbitrary object mu C on the upper half plane. I'm saying that only if that mu C transform in this way, then I can think of that as a Beltrami differential defined with respect to the group gamma.
Otherwise, there will be some ambiguity.
Otherwise, it's not an object on the Riemann surface. That you define in this way, right? It's just a periodicity condition that you want. So if you want to think of a function on if you want to define a function on a circle, you want appropriate periodicity conditions, right? So it's just that.
But also I have a question. So this and these are not really related, because d gamma C by Z, and then you take the complex conjugate of the whole thing, whereas there is a differential. There are two different. It's a differential with respect to Z bar and
So
Z.
see, you have if you want to transform del F C bar to gamma C, how you do that? So you do it by chain rule, right? So that's why it's just a differential, right?
Okay.
Yeah, it's -1 differential. So you have it. So in this way, you can define a Beltrami differential on the upper half plane with respect to a particular Fuchsian model gamma. So this Beltrami differential is a differential on Riemann surface R. So now I want to characterize inequivalent Beltrami differentials or inequivalent quasi-conformal transformation. How will I do that? I can take this Beltrami differential. So assume that you have mu C transforming this way. Take this Beltrami differential and solve the Beltrami differential equation, and then I can obtain a quasi-conformal transformation which I denote by W mu. So I could take another Beltrami differential nu, and then again compute the canonical quasi-conformal transformation W nu. By canonical quasi-conformal transformation, I mean that they satisfy this normalization condition. So when I have omega mu and omega nu, now I have to tell you a specific a criteria which distinguish omega mu and omega nu. So I could take these two transformation and then apply it on the upper half plane. That will induce a change on the, that will induce a or that will change the Fuchsian group. So gamma will go to gamma mu, where gamma mu is omega mu gamma omega mu inverse. So you have such a transformation. So when I perform a quasi, so let's start with the Beltrami differential, find its quasi-conformal transformation, apply it on the upper half plane. That will change the.
What do you mean by applying on the upper half plane?
So take the point on upper half plane, C point on a point Z on the upper half plane.
Okay, so this is just a differential. What do you mean by?
I have to solve it and then get the corresponding quasi-conformal transformation.
F.
Exactly, right.
F has become omega.
Omega. So,
The Beltrami differential. Omega.
or you could think of this as F if it's confusing. This is
Okay.
F.
Okay, now I get it.
Sorry. So F mu and F nu.
Yeah, so given mu, you construct F mu
Yeah.
because it satisfies this condition.
Then take another nu, another Beltrami differential nu. Find F nu. Then I want to see, explicitly spell out a condition that says that F mu and F nu are not equivalent. Or when is F mu is equivalent to F nu? When they are inducing a change on the Riemann surface that can be related by a conformal transformation. So if I can explicitly state it, then I have a better characterization of Teichmuller space. This is what I want to gain.
If I conjugate the Fuchsian group gamma
Yeah.
by quasi-conformal transformation, it still remains a Fuchsian.
It's become a Fuchsian group, provided the Beltrami differential transform this way. So here you can intuitively understand in the following way. So you have a Riemann surface and you define a Beltrami differential on it, and that can generate a quasi-conformal transformation that will change you, that will take you to another Riemann surface. Now the new Riemann surface S can have its own Fuchsian model, right? Which I said call as gamma mu. Yeah. So which I can obtain by doing this transformation. So now gamma mu is a transformation or the Fuchsian group that I obtained by applying the Beltrami differential mu. By that I mean take the quasi-conformal transformation and then apply it in this way. I get the group gamma mu, and then I can also do the same thing for another Beltrami differential nu. Get gamma nu. Now when gamma mu equal to gamma nu, so I'm going to state a result, and don't ask me from where it is coming. It's just a theorem.
I want to ask something very simple. From the point of your Fuchsian group,
Yeah.
group 3 to your point,
Yeah.
you write Jz plus P divided by Cz plus P.
Yeah.
Where A, B, C, D will be
Some real number. Yeah.
real numbers.
That is true. Yeah.
So, what is it? You want to find the subgroups of it?
Yeah, I have a subgroup Fuchsian group, right? So I have the Fuchsian group, and then I can change the Fuchsian group by applying a quasi-conformal transformation, right? If when I apply a quasi-conformal transformation which has this property on the upper half plane, that will give you a new Fuchsian group. And that, so the question is whether that new Fuchsian group is giving you a different Riemann surface or not. Or the new Fuchsian group are they the same as the old Fuchsian group that you had?
Fuchsian group was a subgroup of PSL.
PSL2, right.
So the gamma mu should also be a subgroup.
Subgroup, exactly, yeah.
But with a different Z and Z bar, a different complex structure.
With different complex structure, right. That is true. So both of them will give you a Riemann surface, but they are two Riemann surfaces. Or they may be same Riemann surfaces.
Right. But it's guaranteed that it will remain a fractional linear transform.
Exactly. So this is this one statement you can see intuitively from the fact that this mu is actually a Beltrami differential on the Riemann surface. You should be able to see it from the upper half plane itself, but I don't have any clear intuitive argument for that. So these are things we can algebraically prove easily, but I mean I don't have a clear intuition. So this is one statement where I don't have a clear, simple answer from the upper half plane itself. And the next thing I'm going to say, there also, I don't have a simple statement. I can do algebra and then show that the condition that I'm going to state is the actual condition which is required. So my condition is the following. So I want to take Beltrami differential mu and nu, transform gamma to gamma mu and gamma to gamma nu. I want to ask whether when gamma mu, function group gamma mu and gamma nu are same, when they are same. So the state exactly same function group. That means if gamma mu and gamma nu are same, you will get the same Riemann surface. So you are not able to change the complex structure. When you can change the complex structure, that's the main statement that we want, right? Or when they are equal. Once we get a precise statement, then we have a better characterization of Teichmuller space, right?
So this is all being done from the point of view of upper half plane.
Upper half plane. Yeah. So that's already encoded. Once you say that mu is transforming this way, that's already.
You can apply finally to this to R.
Exactly. Right. So you find the new two function group and ask when they are equal. My statement is the following: they are equal whenever the associated transformation f mu and f nu is exactly equal on the real line. Whenever f mu equal to f nu.
Not just
equal. So this is that's why it's an extremely beautiful criteria. And I don't have I mean you can use the properties of function group to arrive the statement.
The upper half plane goes to the upper half plane.
Yeah, because anyway upper half plane don't have any other complex structure. So it's a unique complex structure, right? So the statement is that whenever quasi-conformal transformation f mu and f nu is exactly equal on R, they will produce. So the Beltrami differential mu and nu will produce the same.
The subgroup of SL2.
Yeah. PSL2R.
PSL2R.
Yeah. So whenever this condition satisfies, mu and nu will not provide you different surfaces. So this gives you a clear criteria for equivalence relation, right? So you take the quasi-conformal transformation on the upper half plane and look the value on the real line. Whenever they are equal, then you don't have to think of them as two. They are actually same. Now this statement can be made more, you can convert it into a more useful form.
Is that example F? K would have been the same.
That example?
F here.
Yeah.
So if you make some other F.
So actually this thing is not a quasi-conformal transformation with respect to any Riemann surface. Right? Because it doesn't have any periodicity. So it looks like okay, the Beltrami differentials are quite simple on the upper half line. These are not quite simple because whenever you impose huge amount of symmetry, that function is not going to be a simple function, right? So the sin x is a nice function, which is again is just a function defined in terms of something else, right? So you see the real definition of sin x. It's a infinite series, right? So whenever you want symmetries for a function, the function is extremely complicated. Although we think that symmetry makes everything beautiful, actually symmetry makes things more complicated, right? At least from the point of view of seeing the explicit forms. So
This is an even and only statement.
this is
If and only statement.
if and if is both ways. So when I can make it into a more useful form. I can convert it into a more useful form. So right now you won't see why it is useful, the thing that I'm going to say, or at least you can. So you see, upper half plane is a nice space, but complex plane is better space, right? So we can apply our understanding about. You can apply this contour argument easily on the complex plane, right? So it's nice if I can extend this study on the upper half plane to the full complex plane. Then I have better power, right? I can use all this Cauchy's formula or the generalization of Cauchy formula to get a better control over the whole thing. So I'm going to state an equivalent definition for Teichmuller space. So here, what is the definition for Teichmuller space? Teichmuller space is the space of all quasi-conformal transformations f mu inequivalent quasi-conformal transformation that you perform on the upper half plane, such that two such quasi-conformal transformations on the real line are not equal to each other. It's exactly equal. So that is the better thing, right? Exactly equal is always better than equivalent. So now you can, so you have, I'm defining the space of, or the take model space for Fuchsian model gamma or Riemann surface R. These two are same space. So the definition is the following. So you look into the upper half plane, consider all quasi-conformal transformation that can be obtained from such a Beltrami differential, and then you say that you want to consider only inequivalent quasi-conformal transformation that you perform on the upper half plane. Now the good thing is that now we have a better way to characterize in the inequivalent class. Whenever f mu equal to f nu, you have to think of them as same on the full upper half plane, or you have to think of them as equivalent. So now let's convert the whole problem from upper half plane to the complex plane. So the similar statement is the following.
So that means you are taking the lower half plane.
Yeah, I'm extending the definition of Beltrami differential on the upper half plane to lower half plane as well. So the definition mu tilde is, so mu tilde C is a Beltrami differential on the complex plane, and the extension is a trivial extension. Whenever C belongs to upper half plane, you say that mu tilde C is mu C. Whenever C belongs to H star, which means lower half plane plus the real line, then you say that the Beltrami differential is 0. It's a trivial extension. So again, one can argue that if this mu is producing f mu and f nu such that they are equal on real line, then they are equal on the lower half plane as well. So now the new criteria is the following. So you start from mu tilde and compute f mu tilde on the full complex plane. Then we say that f mu tilde and f nu tilde are equivalent whenever they are equivalent on complex plane, a lower half plane, and the real line. And this is an equivalent statement. So this is the definition for take Muller space. So
this is 0 on H star and R.
R is a real line. H star is a lower half plane. Lower half plane does not have the real line, right? So that's why I'm taking the full union.
But I thought upper half plane had the real line.
No, upper half plane it does not have the real line, right? It's just upper half plane.
So this is in the limit when you go to the.
Yes. So all.
It's a limiting.
Yeah. Is all. So R is actually the limiting set, right, for the Fuchsian group. That's the boundary of upper half plane.
And if you go to the unit circle, then it is a circle. You are pointed in.
Right. So this one, I mean, it's a definition which is very useful for us. This is a definition which is going to be more useful for us when we do actual computations.
F mu tilde, what is the relation there? F mu tilde is equal to F nu tilde.
F nu tilde on the lower half plane and the real line. Then they are equal. Then mu tilde and nu tilde produces the same Riemann surface. Or mu and nu produces the same Riemann surface. Here you don't. It looks like, okay, why should I do this? And
So you're extending the quasi-conformal transformation also similar
yeah,
to the lower half.
to the lower half plane.
Just say 0 on the lower half.
Yeah, quasi-conformal transformation on the lower half plane is more like C. So it's like a conformal transformation, right?
See, actually, lower half plane and upper half plane are same actually. You can
So
take any of them.
if mu is identically 0,
Yeah.
all of lower half,
Yeah.
then what will be the corresponding?
So this is the statement I make.
That means it's conformal.
Right? It's in the lower half plane. The transformation is conformal.
Identity. You're just identity.
That is.
Yeah. So when I have exactly equal relation on the lower half plane, then it's actually equivalent relation on the upper half plane. Second.
Financial basis.
Yeah, sure. I think I have one more thing to state. Then that.
When you calculate open string scattering, sometimes you do doubling tree.
Yeah. Yeah.
Complexity.
Yeah.
Is it related to that?
I mean, why use doubling? To make use of the complex structure. This Cauchy's residue formula, right? It's something like that. I mean, it's not complex. I'm not using Cauchy's formula because anyway I'm working with quasi-conformal transformations. I'm actually using the Cauchy-Pompe formula. This is generalization of Cauchy formula. Now, all these things have something useful to. These are not some. This can be used for some better for the better understanding or better characterization of Teichmuller space. So the statement is that you found that how to relate or how to make the equivalence relation in an equality relation. So you have an equality relation that represents an equivalence relation.
Simple question. Yeah. You pronounce the Teichmuller space or Teichmuller space?
Or Teichmuller space. Or Teichmuller space. No, so that's an equivalence relation. So maybe I think I can stop if you want. So maybe that's the best thing. I can stop here.
But what's the plan for tomorrow?
If I make one more, if I take 5 more minutes, I can say something interesting. So far, it looks like I'm giving you some definitions, right? And the following statement is more useful. You might be more familiar with that statement. So take this quasi-conformal transformation f mu and then compute its Schwarzschild derivative. So it's easy to see that this one transforms like a quadratic differential.
What are you computing? F
mu c, then I have a bracket. This bracket represents the Schwarzschild derivative. I will explain what is that.
Schwarzschild derivative. Oh, yeah.
Exactly.
Schwarzschild derivative.
So that is defined as, so I have this 3 by 2 del f del c square so let's take f mu nu, do this calculation, you get the object phi mu z, and the statement is the following: phi mu z now will transform like a quadratic differential. So that's something easy to see, right? So you have del c cube here and here del c, so effectively it's like a del square del c square. Here you have del c or del square del c square whole square divided by del c. So that's again like a quadratic differential. So this object is a quadratic differential. Now look, evaluate it and then see what is phi mu z in the lower half plane. In the lower half plane, whenever I have two equivalent mu and nu, two equivalent Beltrami differential, corresponding to that I have equal quadratic differentials on the lower half plane. On the upper half plane they may not be equivalent, but on the lower half plane they are equivalent. So that means the space of all quadratic differential that I define this way can be on the lower half plane can be identified with the Teichmuller space.
And upper half plane they are not equivalent.
So they are equivalent. They are equivalent, but they are not equal. On the lower half plane they are equal when they have equivalence on the upper half plane.
So it's going to inversion symmetry.
It's a
inversion.
Yeah. So now I have I'm identifying a space of quadratic differential that I define on the lower half plane with the Teichmuller space. You might remember that the tangent space of Teichmuller space can be identified with a space of quadratic differentials, right? So you might have seen in Polchinski. So the space of the Teichmuller space or the tangent space of the Teichmuller space can be identified with quadratic differential. Space of quadratic differentials.
Quadratic.
So that statement comes from this observation.
But these
So-
quadratic differentials are defined strictly on the lower half plane,
Lower half plane,
including R.
including R, or you can think that okay, you don't include.
Statement is that if F mu and F nu are equivalent, meaning that they are same on R.
Yeah. Then they are same on the lower half plane as well. So
Yes, that's right, and also phi mu is equal to phi nu.
phi nu, right?
Because anyway F is same.
F is same, right? So that means you are. So let's say the space of all quadratic differential that you define on lower half plane is A to H star gamma, right? So the group gamma can act on the lower half plane as well, right? It can act on the upper half plane, or it can act on the lower half plane as well. So when I perform a Fuchsian transformation on the lower half plane, this object that I computed, phi mu, so it's just a Schwarzschild derivative of quasi-conformal transformation on the lower half plane with respect to C, that transforms like a quadratic differential. So the space of all such quadratic differential I define as A2. This space can be identified with Teichmuller space, T gamma. So this is the statement.
So what does the Schwarzschild derivative do?
It converts a function to a quadratic differential.
Yeah.
On the top of it, whenever I do a quasi,
Because of that they are equal.
exactly, because of that they are equal. Yeah.
Because of lower half plane.
Yeah. So in lower half plane you have equivalence for equality for transformation, right? And also Schwarzschild derivative has the property that when I perform a global symmetry transformation on the complex plane, Schwarzschild derivative just throw it out. Whenever this is a Mobius transformation, the Schwarzschild derivative is 0, right? So that we have a better function, right? So you are not introducing any inequivalence because of the symmetries of the complex plane. So that means you are identifying Teichmuller space with this space of quadratic differential that you define on the lower half plane. Now we have the statement. So now we have an important statement that says that you take this phi mu and then multiply it with minus 2. Some is just 2. Minus 2 is just a factor, which is conventional factor. So take imaginary C and then take a square and multiply phi mu C, multiply it with the conjugate of phi mu C. Here C belongs to upper half plane instead of lower half plane. So this object transforms as a Beltrami differential. See, now the point is that whenever this space of Beltrami differential, each element, so this form a space of Beltrami differentials with a specific form, and this space is known as the harmonic space of harmonic Beltrami differentials. So the space of harmonic Beltrami differentials is defined on the upper half plane. That means on the Riemann surface itself. So whenever all two harmonic Beltrami differential will always generate an inequivalent complex structure. So that means the space of harmonic Beltrami differentials can be identified with the Teichmuller space. So you start with the space of Beltrami differential that you define on the upper half plane. You split it into two: space of harmonic Beltrami differentials and some other space n gamma. This is the part of the Beltrami differential space that we are supposed to identify with Teichmuller space.
So Beltrami, the space of Beltrami is equal to the harmonic
Beltrami differentials and the some null vectors from the point of view of Teichmuller space. So whenever I take one Beltrami differential that belongs to n gamma, that won't be able to change the complex structure. So this is my final statement. So I identify the space of Beltrami differentials, a part of the space of Beltrami differential to the Teichmuller space. So I have a nice space now. Now if I want to define a tangent space or on the tangent space on a point on the Teichmuller space, what I am supposed to do is I can take a particular point on the Teichmuller space, that basically point on the harmonic Beltrami differentials, define a curve on it, then take a derivative with respect to the parameter that I use to parameterize the curve. That will provide me tangent space or tangent vectors That's the statement. Done.
Wait, let's end.
Thank you.